Jai Hind everyone. This is once again Jyoti Sharma in front of you, going to discuss the Aktu University question paper of the year 23-24, which has occurred in the even semester, of the subject Fundamentals of Electrical Engineering, which is a first year course having a subject code of BW 101 under AKTU. In the previous 2 and 3 sessions for the same university question paper, we have discussed section A, comprising of 7 short questions, section B, which is having question number 2, which is having 5 questions having 7 marks each, and section C, we have discussed question number 3 and 4th, each is having 2 parts. And now we are going to discuss the last 3 questions, question number 5, 6 and 7, which are from the units 3rd, 4th and 5th. So moving on with the 5th A question. So the question is a 20 kVA 2000 by 200 volts single phase 50 Hz transformer has a primary resistance of 1.5 ohms and a reactance of 2 ohms. The secondary resistance and reactances are 0.015 ohms and 0.02 ohms respectively. So, the no load current of the transformer is also given, and that is 1 ampere at 0.2 power factor. So, we need to determine the equivalent resistance, the reactance, the impedance which is referred towards primary side. We need to find the supply current, that means I1. We need to find the third, that is total copper loss, and it is also being asked to draw the approximate equivalent circuit of the transformer. And obviously, as the question is for all the parameters which are referred towards primary side, so the equivalent circuit which has been asked is also regarding the referred towards primary side. Okay. So, moving on with the very first question that is being asked, that is equivalent resistance referred towards primary. That means equivalent resistance referred towards primary, that is being given by R1E. Equivalent resistance referred towards primary. Now, that is given by the primary resistance as it is not going to get changed, but the secondary resistance which used to be R2, that is referred towards the primary side, so its value is changed and that becomes R2 dash, and that R2 is given by R2 by K square, right? Where once again, what is K? K is the transformation ratio, and the transformation ratio that is given by V2 by V1, E2 by E1. So, first we need to find how much is K, right? Because we know the value for R1, the value for R1 primary resistance is 1.5 and the value for the secondary resistance, the primary resistance is 1.5 and the secondary resistance is 0.015, right? So, we know the value for R1 and R2, we need to know the value for K. Now, K is given by V2 by V1. What is V2? So, we have to see the rating of the transformer. This is V1, this is V2. So, V2 by V1, that is 200 by 2000. So, 200 by 2000 will be having it as 0.1. So, the value is 0.1, right? So, K is 0.1. If that is so, what is our R1E? R1E is given by R1. What is R1? R1 is 1.5 plus what is R2? The secondary resistance is 0.015 divided by R square. R is 0.1, 0.1 square, right? So, this becomes 1.5 plus this is once again 1.5. 1.5 plus 1.5 becomes 3 ohms, right? So, we get R1E as 3 ohms. Now, X2E, that means equivalent reactance referred towards, X1E, equivalent reactance referred towards primary. Now, equivalent reactance referred towards primary, that is once again given as X1 plus X2 dash, that is X2 by K square. We have already found out how much is K. K is given by 0.1. So, substituting once again, X1 is 2 plus X2 is 0.02 upon 0.1 square. So, it is 2 plus 2, that gets me 4 ohms. So, X1E is now once again given as 4 ohms, right? Then we need to find Z1E, equivalent impedance of the transformer referred towards primary. Z1E is once again given as It is given as R1E plus JX1E, right? What is R1E? R1E is given as 3. We have already found it out. 3 plus J4, right? And if we find out the magnitude of it, under root of 3 square plus 4 square, that will give us 5 ohms. So, Z1E, magnitude wise, Z1E is 5 ohms. Now, these are the 3 equivalent resistance, reactance and impedance referred towards primary. The second question which is being asked is the supply current. How much would be the supply current? To find the supply current, what we need to know? Now, to find the supply current, we need to know second. The supply current, that means I1. Whenever in the transformer, we want to know the rating or the current ratings, let it be the primary or the secondary, we need to always go towards our rating of the transformer. So, the rating of the transformer, that is given as 20 kVA. We know the rating of the transformer is in kVA or VA. That means it is V1 I1 or V2 I2. So, now if at all I see here, how much is V1 I1? V1 is I1 is equals to 20,000, 20 kVA, right? In that case, I may be knowing how much is I1. That will be given by the rating divided by V1. And how much is V1? We know V1 is 2000. So, just going with this. So, we are having it as 10 amperes. So, the current, the primary current in the transformer, that is being given as 10 amperes I1, right? Now, finally, the total copper losses in a transformer. The total copper losses in a transformer can be given with 3 formulas, in fact, right? The very basic formula which can be using for finding total copper losses, we used to call it as PCU. Obviously, this is at full load. This can be given as I1 square R1 plus I2 square R2, where in this case there is no referring, where what is R1? R1 is the primary resistance and R2 is the secondary winding resistance, right? Now, if at all I referred the secondary resistance towards the primary side, now at that case I may be having the another formula which is given by I1 square into R1E, right? What is R1E? It is the same equivalent resistance referred towards primary. Similarly, if at all I refer the complete circuit towards the secondary side, I may be knowing it as I2 square into R2E. I may be finding it off with any of the 3 formulas, right? But the most feasible one, which is being more practical in this particular case, for this particular numerical, we already know how much is the value for R1E, right? We have found it off. R1E is given by 3 ohms. So, if R1E is 3 ohms, in that case, we may be knowing. Now, we have already found out how much is I1. So, we can be finding the value for total copper losses as I1 square R1E. What is I1 square? I1 square is obviously 10 square into R1E, that is 3. So, that becomes 300 watts. So, the total copper losses for the transformer becomes 300 watts. Now, the second question for the same unit, for the same question, 5th question, that is explain the working principle of the transformer and also derive its EMF equation, right? So, we need to explain the working of the transformer, working principle of the transformer. So, first we need to define what is the working principle for a transformer. So, I must say the working principle of transformer is nothing but mutual induction. And whenever the induction is there, it has to be, this will be in fact followed by Faraday's law of electromagnetic induction. In fact, this is one of the law of Faraday's law of electromagnetic induction, right? What is mutual induction? Now, we need to explain this principle being applied to the transformer, and for that we need to have a core type transformer to be displayed. This is the transformer which we generally use for explaining the working because the working can be easily explained with this kind of transformer. Fine. So, this is the primary of the transformer which is being fed with certain AC supply. As we know, the transformer works with only AC. So, we'll start. Once we give an alternating supply to the primary of the transformer, there will be an alternating current flowing in the primary winding, right? Now, the primary winding is having certain number of turns in one. That's why the transformer will be having a sufficient MMF, right, which is sufficient to produce. The MMF is the force, which is the driving force, which will be producing the flux, right? Now, as the current is there, number of turns is there, we'll be having the flux being produced in the transformer depending upon the current direction, right? Say the current direction is, say, upwards. Now, according to the current direction, say this is the flux. As the current is alternating, the flux produced will also be alternating. It will also be sinusoidal in nature, right? So, as the flux is changing by itself, I am getting a d phi by dt. Rate of change of flux will be there. It is alternating. It is sinusoidal, right? So, whenever there is a rate of change of flux, we'll be having an induced EMF. That is nothing but the Faraday's law of electromagnetic induction. So, when this alternating flux links with the primary coil, it will result in an induced EMF in the primary winding itself, right? But because this is because of its own supply, the induced EMF what we are getting in the primary winding, that is because of its own supply. That's why this E1, which is the self-induced EMF in the primary winding, this is self-induced EMF. So, we'll be saying there will be a self-induced EMF in the primary winding because of this alternating flux, okay. Now, when the same flux, because we are having a common core connecting the primary and the secondary winding, when the same alternating flux links with the secondary winding as well, because once again the nature is alternating. When it is linking with the secondary coil which is being placed nearby, which is magnetically coupled, there will be a induced EMF in this winding as well. But in this case, say I am calling it as E2, this induced EMF will now be called as mutually induced EMF. Because this induced EMF is because of not its own supply, it is because of the supply, because of the flux which has originated from its nearby coil, right? Or a supply which has been given to its nearby coil. That's why, because of the mutual induction effect, there will be an induced EMF in the secondary winding. Now, if the secondary winding circuit, if the secondary circuit is completed and it is being connected with a load, obviously this induced EMF will be driving the secondary circuit. It will be making a current to flow through the load, and there will be a terminal voltage which will be occurring across the load, which we call it as V2. That's why we used to explain the complete working of a transformer. Once again, in one go, when we give a single phase AC supply to the transformer, there will be an alternating current. This alternating current will be giving us the required MMF, which is required to establish the flux in the core. As the nature of the flux is also alternating, it is sinusoidal in fact, because according to the Faraday's law of electromagnetic induction, whenever there is a rate of change of flux, we'll be having an induced EMF. The transformer primary will be having a self-induced EMF in the primary winding. Now, the same flux, the same sinusoidal flux is linking with the secondary as well. Because of the mutual induction, we'll be having a mutually induced EMF in the secondary winding as well. Now, the secondary induced EMF, mutually induced EMF, will drive the load circuit, will make the secondary current to flow through the load circuit, and the terminal voltage will also occur across the load. So, this is the working principle. Now, the second portion in it is we need to derive the EMF equation, right? Now, the EMF equation of the transformer, it can be derived. We'll be starting with the alternating flux. We have just seen as the transformer will encounter an alternating or a sinusoidal flux. As we give a sinusoidal supply, the current is alternating. The flux which will be generated will also be sinusoidal. if that sinusoidal, the instantaneous value of that sinusoidal flux is given by some phi m sine omega t. This is the way how we represent any sinusoidal quantity. So, the flux can be represented as phi is equals to phi m sine omega t. Now, according to Faraday's law of electromagnetic induction, because we are talking about the induced EMF, E1 and E2. So, according to the Faraday's law of electromagnetic induction, the induced EMF is given by d phi by dt. In fact, minus n d phi by dt, where n is the number of turns which is occurring there in case of windings. So, if that is so, it will be given by minus n d by dt of this phi, which is the instantaneous value, phi m sine omega t. If that is so, it is given by minus n phi m sine omega t can be written as cos omega t, the differentiation of it, right? Now, once again, cos omega t can be written as sine omega t. I just forget over here. Here it will be omega. And this can be written as sine omega t minus pi by 2 plus pi by 2. But once again, we are having minus here, right? This is a negative phasor. To make this as positive, can be once again be writing it as omega t minus pi by 2, right? So, this is our induced EMF. That is given by minus n omega phi m. Now, this becomes positive. We have reduced this. So, this becomes n omega phi m sine omega t minus pi by 2. From this very equation, we came to know that the induced EMF will lag the flux by 90 degree, right? Now, if that is so, some instantaneous value is given by E is equals to some maximum value sine of omega t plus or minus phi. So, what is the maximum value over here? What will be the maximum value of the induced EMF? It will be n omega phi m, isn't it? This is going to be the maximum value sine omega t plus or minus phi. So, the maximum value is n omega phi m. But when we are representing E1 and E2, these are not the maximum value. These are the RMS value of the induced EMF in primary and the secondary, right? If we want to have the RMS value, the relationship is E RMS would be given by maximum by root 2. So, we need to divide this with root 2, right? So, this is once again n omega can be written as 2 pi f phi m by root 2. When I find out the value of this would be 4.44. I am writing it at the top. It will be E RMS would be 4.44 f phi m n. So, this becomes the expression for the induced EMF in a transformer. That is 4.44, which is given by 2 pi by root 2, if at all I find out the value for this, and then n f phi m. So, it is 4.44 f phi m n. Supposingly, this is the general expression. If I say even is the induced EMF in the primary, even is the induced EMF in the primary RMS value, it can be given as obviously 4.44 f phi m, and the number of turns is given by n1. Similarly, if at all I say E2 is the induced EMF in the secondary, it will be given by 4.44 f phi m n2, as n2 is the number of turns in secondary. And the generalized expression can be given as what we have discussed. So, that is the induced EMFs for the transformer. Moving on with the next question, that is, explain the working principle for a three-phase synchronous motor and also explain any one starting method of the synchronous motor. What is the working principle of a three-phase synchronous motor? Now, the working principle for a three-phase synchronous motor is magnetic coupling. The working principle is magnetic coupling. And what do we understand with magnetic coupling? Magnetic coupling is, it is something like we are having two strong magnets which are being made closer to each other, right? So, there exists a strong force of attraction between the two having opposite poles, right? And if at all I make any one of the magnets to move towards any one direction, the another magnet will also follow it with the same speed in the same direction, right? That is magnetic coupling. That means their magnetic axis has been aligned, right? So if the magnetic axis has been aligned in for both the poles, there will be a magnetic locking or magnetic coupling. In fact, this is magnetic locking which will be occurring. This will be magnetic, not coupling, this is magnetic locking. Magnetic locking. So there exists a magnetic locking between the two poles, right? If their magnetic axes are being aligned, their magnetic neutral axes are being aligned, there will be a magnetic locking. Fine. So how does a three-phase synchronous motor works with this principle? So let's have a synchronous motor being drawn. Say this is the stator of this three-phase synchronous motor, right? If this is the stator, this would be fed with the three-phase AC supply. Three-phase synchronous motor is a doubly excited motor, right? It is a doubly excited motor. Its stator as well as the rotor both would be excited. The stator would be excited with the three-phase AC supply, and its rotor, say if the rotor is a salient pole, for study we used to go for a salient pole, and it is being excited with DC supply. Now what used to happen? As we give a three-phase AC supply to the stator, there will be a production of rotating magnetic field, right? There will be a production of rotating magnetic field which will be rotating at a speed of ns given by 120 F by P. Say the direction of the rotation is clockwise. In fact, the direction depends upon the phase sequence of the supply what we are giving, the three-phase AC supply. Say that is clockwise, right? And while doing that, presently, the poles which are being formed in the stator is, say, here we are having south and here we are having north pole for the stator, right? And as we give a DC supply to the rotor, the poles being created, say, are north over here and south over here, right? In this particular case, it can be seen now, these are the opposite poles. Here it is south, here it is north, here it is south, here it is north. So, we are having opposite poles made closer to each other. And if that happens, that their magnetic axes are being aligned, right? If the case happens that their magnetic axes are being aligned, in that case, the magnetic coupling occurs, magnetic locking occurs, right? So, if the magnetic locking is done, now what will happen? The magnetic locking, again I am saying if magnetic locking is done, right? We'll be seeing whether this locking takes place so easily or not, right? So, if the magnetic locking occurs, obviously, now what will happen? This rotating magnetic field will drag the rotor into synchronism. Initially, it is not rotating. The rotor is not rotating, right? It is just being fed with a DC supply. Now, if the magnetic locking occurs, the rotating magnetic field will draw the rotor into synchronism and will make the rotor also to rotate in the same direction with the same speed, which is 120 F by P, which is nothing but the synchronous speed. That is how a three-phase synchronous motor has to work, right? But does it work exactly like that? Now, what used to happen? This is not, in practical, it is not sure that the rotor placement would be like this and the magnetic axis would be aligned for the stator and rotor, right? The positioning may be different. The positioning may be like this, right? Say this is the stator, right? The stator poles are, say this is stator pole, this is north, rotor pole, stator south and north, and the rotor may be placed like this. And the poles here may be north and south, right? In this case, if at all I see, once again, we are having opposite poles being placed nearby, but the magnetic axes are not being aligned. So, what will happen in this case? Once you give a three-phase AC supply, once again, the rotating magnetic field is there. That's why the poles have been created. The DC supply will create the rotor poles as well. But there will be a strong force of attraction between the two, right? Which will drag this rotor towards the clockwise direction, right? The south pole will drag this rotor towards itself. This north pole will drag the south pole towards itself. It means the rotor will try to rotate in the clockwise direction. But as soon as it tries to overcome the inertia, till then, instantly the poles of the stator would be changed. at the very next instant, the poles would be changed for the stator because it is a rotating magnetic field. In this case now, the poles would be north, south and now this time they will be as it tries to rotate in the clockwise direction, this will once again be north and this will once again be south. The poles will change. Initially it was south, it will be changed to north. Initially it was north, it will be changed to south. In this direction now what will happen? These two are the common poles, right? They will repel each other. These two will repel each other. Now the rotor will try to rotate in anti-clockwise direction. Now once again, once it tries to rotate in the anti-clockwise direction, once again the first condition will occur, right? These stator poles will once again change. This will be now south pole, once again the force of attraction. So it will once again be rotating in opposite direction. So the rotor is not able to rotate in any one particular direction and is not able to overcome the inertia in one particular direction. That's why a three-phase synchronous motor is not self-starting. It is not able to come up to the magnetic locking. The magnetic axis of the rotor and stator are not being locked, right? They are not being aligned. Now what we can do, another question with this is, what can be done to have the locking? That means how can they be started, right? There are various methods by which it can be started. One of the method is by using pony motors, small AC motors, by using pony motors. And the other method is by using damper winding. The third method is by using DC exciters. The fourth method is by using three-phase slip ring induction motor, right? So we are going to discuss, as the question is being asked to discuss only one of the method, we are going to discuss damper winding, how it is going to work with damper winding. Now, what is a damper winding? What we used to do in this case is, right, say this is once again this is the stator and this is the rotor. What are damper windings? In extra to the main DC windings, these are the DC, the main rotor winding. In extra to that, we used to provide one more winding in the rotor poles, right? They are embedded inside these pole shoes, right? And they are being actually having the copper bars being inserted at the pole shoes, which used to make it to look like exactly the same construction as that of a squirrel cage rotor, right? The rotor, the windings give exactly the same replication of a three-phase induction motor with which kind of rotor? A squirrel cage rotor, right? And initially, we don't give the DC supply here, right? We don't give the DC supply. There's a switch being connected. Now, when we give a three-phase AC supply to the stator, what will happen? Once again, once you give a three-phase AC supply to the stator, there will be a production of rotating magnetic field. The rotating magnetic field would be produced, right? Which will be rotating with the speed of ns, okay? Now, as we haven't provided any of the DC supply, the main poles will not be, the rotor poles will not be created, right? So, we are only having the stator poles. Say this is south and say this is north, right? Now, we are having one more winding which is being called as damper winding in the rotor. So, the rotor conductors, these are stationary, they will experience the flux cut because of the rotating magnetic field, right? As they experience the flux cut, there will be an induced EMF. Once the induced EMF is there, they will be experiencing current because these are short-circuited rotor conductors. Once the current is there, they will be experiencing torque, right? So, the rotor will rotate in the same direction as that of rotating magnetic field, but with the speed, now the rotor will rotate, but with the speed nr, which is slightly lesser than ns. That means we are making the rotor to rotate with the speed which is almost equals to ns, without any poles being created right now. Now, when the rotor is rotating, right, the rotating magnetic field is also there. The rotor is rotating with almost the same speed as that of ns. Now, when we switch on the DC supply, the rotor poles would be created, right? So, at one instant, because now it is rotating, right, at almost the same speed, at one instant it will happen that we'll be having a north pole being created here and a south pole being created here. There will be a magnetic locking occurring between the stator and rotor poles. Once the magnetic locking occurs, once the magnetic locking is there, the rotating magnetic field will drag the rotor into synchronism and will make the rotor to rotate with the same speed as that of ns. Now, it will continuously rotate with the speed of ns. That is what is required. Now, what will happen to the damper windings, which are already there? Now, the damper winding, as it is working exactly like a squirrel cage induction motor. Now, the speed of the rotor is equal to ns. Now, there is no relative motion between the damper winding and the rotating magnetic field. So, if there is no relative speed, there is no flux cut experienced by the rotor conductors. There will not be any induced EMF, no current, no torque, right, by the damper winding, right? But the rotor is continuously rotating because the magnetic locking has been done. The rotor is continuously rotating with the speed of ns. The damper winding is there in it as it is. This kind of starting, in fact, this kind of starting gives us a lot of copper loss because we are using copper bars, and this makes the rotor circuit bulkier also. That's why this method is lesser used. Generally, the used methods are methods by pony motors, where we used to connect an external motor which is running, making the rotor to rotate with the same speed as that of ns, right? So, the second question with this is, draw and explain the torque slip characteristics for a three-phase induction motor, indicating the starting torque, the maximum torque, and the operating regions. Now, the torque slip characteristics for a three-phase induction motor, it can be given like this. This is the maximum torque. The slip corresponding to the maximum torque is given by R2 by X2. This is the slip at starting, which is 1, right? So, this is nothing but the starting torque. Our full load torque is somewhere here, right? We can also indicate the speeds. Here the speed is 0, here the speed is equals to ns, and this is in between. Now, the three regions which is being asked, here is the starting torque, which we have represented, the maximum torque, and the operating region. This is actually the low slip region, which is also the operating region or the stable region. It is also being called as stable region. And this region, which is the high slip region, this is also being called as unstable region. Now, in this case, if we just see, in case of lower slip region, in this case, the torque is directly proportional to slip, right? In this region, where the slip is towards 0, lesser slip region, lower slip region, where the slip is towards 0, between 0 to Sn, in this case, the torque is directly proportional to the slip. If the torque is directly proportional to the slip, this makes it region in the stable one. Why this is so? Say, if at all, the load is being changed. So, the load is being increased. If the motor is operating in this range and the load is being increased, right? The load is being increased, the speed of the motor will decrease, right? If the speed of the motor will decrease, the slip will increase, right? If the slip increases, with that, what will happen? As the torque is directly proportional in this particular region, as the slip increases, the torque will also increase according to the increased load demand, right? So, this region is being called as the stable region or the operating region. Whereas, in this high stable region, what is happening? In this high stable region, we can, high slip region, which is moving towards 1, in this particular region, we can be seeing that if at all I increase the load, the speed will decrease, the slip will increase. But In this particular case, the torque is inversely proportional to the slip, right? So, if the slip increases, the torque will decrease. That means the motor, which is supposed to make more torque compared to the increased load demand, is not preparing that much torque. It is in fact decreasing. So, the motor will feel even more loaded, right? So that the speed decreases, the slip increases, and once again, it is inversely proportional, the torque will further decrease, right? So that's why this region is being called as unstable region, right? This is the maximum torque. The condition for the maximum torque can be derived with the expression that the torque of the motor is proportional to S times R2 square, S times it is being given as Ks E2 square R2 divided by R2 square plus Sx2 whole square, where K is given by 3 upon 2 pi small ns, right? This is equals to. In that case, if at all we want to have the expression for, or I must say the condition for the maximum torque, we can differentiate the torque with its function. The torque is a function of slip. If we differentiate it with respect to slip and equate it to 0, we'll be coming to know Sm is equals to R2 by X2. So this is the maximum torque being produced at the slip R2 by X2. The last question which is remaining, that is, explain the construction of a cable with suitable diagram and write each layer. What is the use of insulation layer and metallic sheath? So we can be seeing over here that the general construction for a cable, so the general construction for the cable can be given with this 6 layers. We are having conductor. The conductor, which is generally, it can be stranded conductors, it can be single cord, it can be double cord, it can be 4 cord. Then it is generally made up of copper or aluminium. It can be steel reinforced conductors, ACSRs conductors. Insulation, the insulation layer that is generally being provided with the PVCs, or it can be provided with rubber, right? It can be vulcanized Indian rubber, but if it is a vulcanized Indian rubber, it will be tinned, right? If it is a tough rubber, then the tinning is not required in that case. It can be provided with PVC as well. Then lead sheath, that is a proper sheath of a lead. It is generally a metallic sheath which is being provided for providing a better mechanical support and to protect the cable from external factors like from fire hazards or from moisture from the air, right? Then the bedding is being provided because the lead sheath is already there, right? And to provide a better the insulation between the lead sheath and the armoring, the bedding is being done. This is generally being done with the help of fibrous material like jute or impregnated papers, right? Then armoring, it is the steel armoring. Generally, it is steel armoring which is being done. It can be a steel braid armoring, it can be steel wired armoring, it can be or the another alloys of the steel, they can also be used for steel armoring for providing a better mechanical support to the cable. Then the final serving is generally being provided with the rubber or with the PVCs. So this is the general construction. The use of the insulation layer which we have seen, they provide the protect the cable from the various external factors like air, moisture, the chemical reaction, the fire hazards, right? The atmospheric changes which are occurring, and also protect it from the temperature changes, right, which are occurring outside. And in fact, because the cables are carrying a heavy load there, so it protects it from those heavy currents which are flowing. Then the metallic sheet that provides once again a better mechanical strength to the cable. The last question that is being asked is, what is lightning and what is the best lightning protection? So if at all I say lightning, it can be explained in terms of the charges which are being produced due to the rubbing, as we can see it in, at our homes also. So during a thunderstorm, the current, the air currents, that they move upwards and the water droplets, they move downwards. And this is caused due to the separation of the charge due to the vigorous motion, right? So as a result of this process, the positive charges, they collect near the upper edge and the negative charges, they accumulate near the lower edge of the cloud and also near the ground as well. So as the charge they gets accumulated, its magnitude becomes very large. Now these water droplets in the air, they act as the conductor of this charge, right? So these charges, they flow to meet, thus providing the strikes of the lightning and the thunder. For this phenomena to occur, obviously a sufficiently high electric potential between the two regions and a high resistance medium must be present, right? So this is the lightning. The lightning protection, it can be, we can be providing various kinds of lightning protections. The general conventional Franklin rods are being used. The meshed method conductors are being used. The Faraday's cage method is also being used. Then early streamer emission type air terminals, these are also being used as one of the protection has been asked. So the very conventional way, very general type of lightning protection which is generally being used is the conventional Franklin rods. First known lightning protection system in the modern areas that was meant very originally and was invented by Benjamin Franklin. So this type of lightning protectors were made up of typically like 6 meters of high tapered copper rod, right, which covered the structure. The structure is generally, that is households, or it can be chimneys, or it can be the watchtowers, or it can be the gardens, it can be the low-rise buildings, right? So, these tapered copper rods which covered the structure in order to be protected, and these rods were connected to two separate down conductors and the two earthing systems as well, because these needs to be connected to the earthing as well. Now for the protection radius of such type of lightning air protection rod was very strict up to 30 meters in the radii. So it is obviously only can be used for the protecting small structure areas or the zones, as we have discussed. Those zones can be households or the chimneys, the water tanks, small rise buildings, not very much high rise buildings. This is the construction which is generally being used as the lightning rods, and then a wire is being connected through it and is being made grounded near about the house or the installation nearby within a meter or a 2-meter distance. So this is the final AKTU solution from question number 1 to question number 7, which has been discussed for the year 23-24 even semester. Thank you.